Hey, what's up everyone? My name is Jason Turley. In today's video, I'll be showing how to create a file, how to write to it, and how to read from it in a Linux environment in the C programming language. So without further ado, let's open up tmux. That's optional, but I like using it. Let's create a file. I'm gonna call it fileio.c. And let's build out the main structure that every C program has. They all need a main function that returns an integer. 0 typically means success. And before I start coding, it's good practice to add some comments of what I want to do. So let's say open a file for reading and writing. Write to the file. And finally read from the file. All right. In order to open a file, let's look at the man page for the system call called open. Oh, that's not the one we want. Man2 open. There we go. So there's different sections of the man pages. Just doing man open gave me a different program. That's not what I wanted. I want man2. So I can do man real quick. And we see here that the manual pages have 9 different sections. It'll automatically look for the first one, but we want man2. We want system calls. We want things that are provided by the kernel. Hitting left arrow, go back to man2 open for the system call. It gives us the function that we'll need to include, so we can just grab that. All right, we see 2 different functions for open. One takes the path name and the flag, and then the other one takes that, and additionally it takes the mode. So we can scroll down and read what those do. Opens the file specified by path name. If the file does not exist, we can create it with the ocreate flag. The return value is a file descriptor, a small non-negative integer that is an index to an entry in the process table of the open file descriptors. Then it says we can use these file descriptors for other system calls like read, write, lseek, and function.ctl. So to get started, let's do that. Let's create a file descriptor. I'm just going to call it fd for short. Fd equals the result of opening a file. What should we name it? I'm just going to call this myfile.txt. We want to create it. And we also want to be able to read and write. So I'm going to add option read write. To do that, add the pipe. These are just macros for bitwise expressions that we can see right here. So you can chain them together with the pipe. Scrolling down to the man page, we see all the different flags. And then here is the different modes. We want the user to be able to read and write, so I'm gonna add these 2. Let's zoom out just a tiny bit so we can see it better. One for reading, one for writing. All right, just for reference, let's write down the different file descriptors. fd0 is standard input. fd1 is standard output. fd2 is standard error. So if I want to print out the value of this file descriptor, my fd equals decimal fd. In order for this to work, I need to include standard IO. All right, let's compile this with GCC and then rename it file.io instead of having the object file be named a.out. Hit enter, run the program, and our file descriptor is 3. And that makes sense, right? If 0, 1, and 2 are already taken in that file descriptor table, it makes sense that the next one would be 3. And then if we were to keep going, it would be 4 and 5 and so on. All right, that's cool. But how do we actually write to the file? How do we write text to this file? Well, we can use the write system call that we saw in the first video. Write to our file descriptor. We want to put a message. I'll just say, please sub with a new line. And next we need the length, how many characters to write. So we can count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, plus the new line is 12. Save it, recompile. We get a warning. Let's see if that worked anyway. ls. We see something called myfile.txt, lstech on that. It's not empty. We see that only my current user can read and write from it. Let's cat it out. We see its size 12 bytes. And it worked. Please sub. If we want to get rid of this warning, we can look at the man page for write. All right, man to write. And then we can add uni std. So we can rerun the program, file.io, cat out my file, and it works. There's no error, there's no warning, it's all clean. So that's how you open a file, that's how you write to it. One critical thing we forgot is after you open a file and create your own file descriptor in that table, you need to close it. It's not really big of a deal here in this tiny program that only does one thing, but if this was a server application, something that was always on, always running, like a website, resource allocation matters, so you don't want to just keep opening things without closing them. We'll get into this more in detail when we go over memory allocation on the heap. All right, next we want to read from the file. So let's look at the manual page for read. We need uni std. We already have that for write. It returns s size underscore t, size type, which is basically just an integer. It takes a file descriptor, some type of buffer to store the information, and then, hey, how many bytes should I actually read? So we can do that here. Let's create our buffer of size 20. That's more than enough for our small file. Let's also create another variable called bytes read. Bytes read equals the result of reading from our file descriptor. Into this buffer, we want to read all 12 bytes, the entire file. We can print out the number of bytes read just for debugging purposes, just for some good info. Save, come over here, let's compile and run. And we get bytes read equals 0. Why is that? Before I give the answer, let's look at the man page one more time. Let's look at the return value. It says on success, the number of bytes read is returned. 0 indicates end of file. So we got 0. So we got end of file. The file position is advanced by this number. It is not an error if this number is smaller than the number of bytes requested. So what happened? Let me cat out my file. So if you can see my cursor highlighting it, so essentially every file has a pointer, kind of like the pointer of my mouse cursor right here, and it's used to keep track of where to start reading from, where to start writing to. So earlier we had a write call, right? So we wrote out all this info, all 12 bytes, and then our cursor is here. Our cursor is at the end. So when I try to read from the file, there's nothing to read. So I need to reset my cursor back to the beginning. And we can do that with the lseek system call. Reposition read-write file offset. So once again, it's in that same library that we already have included. It takes a file descriptor, some type of offset, and whence. So it gives these macros, it gives these nice variables that you see in capital letters. These are basically shortcuts. For seek set, go set to the offset. For current, go to the current location plus the offset or go directly to the end. So after we write, we want to reset the file position. So go right to the beginning. Let's see if that works. Recompile and run. Now we see that bytes read are 12. To confirm this one more time, we can print out our buffer. And it prints out please sub, as well as the number of bytes read. Alright guys, here I am in Microsoft Paint just because I want to explain that point a little bit better. So here's the contents of that myfile.txt. Please sub with the new line highlighted there. So like most things in computer science, the first index, the first position right here where this P is not actually index 1, it's index 0, because programmers, computer scientists, hackers, they start counting at 0. The L is at position 1, the E is at position 2, and so on and so forth. The exclamation point is at 10, and the new line is at 11. And then there's like an invisible end of file right here, a null terminator end of file, however you want to picture it, that is at position 12. We also had a few system calls. I'll add those here. We had to write to our file descriptor the message please sub. Which is 12 bytes long. So if I were to highlight this in yellow, write starts here at position 0, and it writes 12 bytes all the way to the end right here. So then the new position tracker is here, is at the end of the file. And that's why when we go to read from that same file descriptor into our buffer, 12 bytes, it doesn't actually work if I make read indigo. That's because it tries to read from here. It reads from the end. That's why I returned bytes read is 0 and nothing printed out. If we use the lseek system call, that'll return to the very beginning. That'll return to position 0 right here. So later on, when we go to read, it reads from the beginning and prints every single byte, every single character out. So there you have it. I hope that made a little bit more sense. Let me know in the comments below. So there you have it. That's how you create a file, write to it, return the file position tracker to the beginning with lseek, and how to read from a file and print out the standard input. Hopefully that wasn't too confusing. Let me know in the comments below what you guys thought, any tips or tricks you guys have. As always, take it easy and see you guys in the next video.